Okay, just to recap what we learned so far. So far we are at chapter 2, finite control volume analysis, and we look at continuity equation. So continuity equation, the famous one is these slides. All right. So remember what we're looking at is conservation of mass, and then from conservation of mass itself, we can derive the continuity equation. So conservation of mass actually is talking about what is in equal to what is out, focus on the mass. And when the mass flow into the system, it must be same. What is in must same as what's out. So this Reynolds transport theorem here, it tells you basically focus on m dot, which is mass flow rate, m dot. And the parameter we use to derive the m dot is rho, density, and volume, and the velocity, okay, and time also, and time. So we have four parameters we use to measure the m dot or the mass flow rate. So the system mass flow rate on the left hand side will equal to what happened on the control volume CV, and plus what has happened to the control surface. So you have two dimensions that you need to consider when you answer question for chapter 2. And when you define conservation of mass, you just equal the right hand side equals 0, which is the total m dot or mass flow rate in the system will equal to 0. So it means that when you consider continuity equation for a non-deforming control volume, so up to today, we were still studying non-deforming fixed control volume. Next lecture, we're going to look at deforming or changing control volume. Okay, so when you have a non-deforming and fixed volume using continuity equation means you equal 0 for the control volume and control surface. Okay, let's look at the first example for today, which is similar to your tutorial question number 5 in your handout. You can download this one in your Moodle. All right, so let's look at a question. So given the inner works of dehumidifier in the photo that you see on your screen. So what does this dehumidifier? It means that it removes humidity in the air. So it make the air a little bit dry, especially for tropical country like Malaysia, and also for Taiwan. During summertime, then you have a loss of humidity in the room, and you need to remove it so that the ventilation will be better. Okay, so the moist air is a mixture of dry air and water vapor enter into the machine at the rate of 300 kilogram per hour. Liquid water drain out of the machine at the rate of 1.5 kilo per hour. So the scratch is given below here. So the diagram here is extra diagram from the textbook example, or usually in the exam you will see only 2D diagram, right? 2D diagram. So what has happened here is that if you look at the machine 2D diagram, the air will come in from the left, and then you go through some coil here, then with the fan that push the air to the right. So you have an in and out, and then as the system operate, some condensation happen, and the water will collected at the bottom, and there is one outlet here that you can drain the water. Okay, you can drain the water. So you have a few opening in the system. Before you solve the question for chapter 2, you need to be sure about your opening, because your opening can tell you whether it is inlet or outlet. So you look at this question on this diagram on the right hand side. On the left, the air is sucked into the system. So this one will become your inlet. You have one inlet labeled as section 1 is your inlet. And then you look at the right hand side here, section 2, this is your outlet. The air will pump the push out from the system. We call it outlet here. And you look at section 3 here. Section 3 here also another opening. So the water will go out from the system. Water will go out from the system that will contribute to another outlet. So you have 3 outlets there. Okay. So when you study about the continuity equation just now, we look at volume dimension and also surface dimension, control surface dimension. So you have the rest is closed because there's no air that coming out from the wall. So you are okay. So you need to focus on the what can the air moving, especially section 1 going in, section 2 go out, section 3 go out. Okay. Now the question asks us to determine the mass flow rate of the dry air, which means here. So the humidity air is from the left. And then when it come out, M2 is a dry air, M3 is water. So what is going out must same with what going in, means that M1 dot must be equal to M dot 2 plus M dot 3. So these two is, when you sum up these two, it will equal to this one, right? Because of the continuity equation that we apply in this example. So we need to determine the mass flow rate. Mass flow rate is our Q. Q is our Q equal to VA. Is a common equation for this chapter. So mass flow rate Q equal to VA. So when you look at the flow rate, this keyword, you should able to write the general equation for flow rate. You write flow rate equation, there will be 1 mark for you to demonstrate you understand what is flow rate calculation. And water vapor leaving the humidifier. So let's try to solve this question. Okay, so I already highlight all the important words here given by the question. You have mixture air, you have water, and you have a dry air coming in and coming out from the system. And as you can see here, there's a M.4, M.5 here. Okay, so this question can be complex or simple, depends on whether the question want to ask you, does it include these two M4 and M5, because M4 is actually a cooling agent, that go into the coil here, that makes the moist air to condense some water, to convert the moist air to water and dry air. This is the internal flow of the condensation pipe here, M4 and M5. Okay. All right. So sometimes when it comes to final exam, it will be try to ask you more complex question. For example, he asks you to test whether there is what happens if you have a leakage of M dot in a system. If your M4 is higher than M5, means that what is M5 coming out here is less, so that there's a leakage in the system here. However, for this one, we will go for simplified cases. So first steps, you need to identify the control volume, inlet and outlet. So if this one is your test question, first you go to the diagram, or you can copy the whole diagram, the 2D diagram, and then draw the first control volume. It means you go to the diagram and confine your interest area with dashed line. So in your diagram, you show an area that you want to study. So if you draw this line, you will get 1 mark in the diagram. Okay. So of course, if you don't draw, then you miss the 1 marks also. Okay. Then inlet. So this is your inlet, section 1. You know that air is coming in. This is your inlet. Outlet. You have 2 outlets here. This one and this one. So if you label this one inlet, you label these 2 as outlet. Sorry for my writing. You will get another 2 marks here. 1 mark here, 1 mark here. So by just defining what you're understanding about control volume, inlet, and outlet, you have 3 marks in your hand already. Okay. And after that, in our case, the motor, the fan, the accessories, the coil, the refrigerants are not included in the control volume. In our case, we do not consider what is happening in the motor, fan, and all this. So as you can see here, when it comes to second statement, you need to taken out, or you need to follow the shape of all the machine. Okay, so if you only consider the first one, meaning when you draw the first one, what is the control volume will look like? It will look like this. This is the first statement. It means you will cover everything. However, if the question will mention you need to you don't need to consider motor, fan, condenser, and all the accessories in the system, then you need to go down to plot all this formula. Okay, so this is how you solve the question. First, identify control volume, identify where is your inlet outlet, and then what is not included in your study area. Okay. Once you have all this already, then you need to also assume something, right? So you go back to the question here. The question here, it doesn't mention about steady flow. So this is a very bad question, not a good one. However, it's still able to guide you through the application of the equation. Normally, the question will state this one to help you to solve a bit faster. And this is a very important statement, because we need to, if you have a steady flow, then it will simplify the equation. The flow rate in section 1, 2, 3, you mean here, here, and here, will be steady flow. Okay, so every time you have the steady flow, the control volume dimension you can take out, or you need to just score yourself some marks. You need to draw an arrow, write steady for the CV component equal 0. That you get 1 mark for applying the steady flow definition. Okay, next, we just write the continuity equation. So you write continuity equation, integration of your CV, control volume, plus the integration of control surface. And what is important is that there's a difference between the volume and the velocity. So if this one is your test or exam, be careful in your answer. So if you write dV for the first one, and the second one you continue to write like this. So I assume this one is velocity. So the continuity equation marks will be 0. I'll give you wrong for the equation. So you'll miss 1 mark for general equation. Take care. Take note on the notation that you use for equation. All right. It's easy to score marks for this module, and it's also easy to lose mark also. So be careful on the notation. All right. And this one is a dot, and then there is a vector sign above the end here. So once you write the continuity equation with the control volume and control surface equation equals 0, then the next one, by automatic, you should know how to score marks already. So just draw an arrow on the control volume dimension, write a steady there. You can cancel out this one and make sure you look for this statement. Okay, look for this statement. And of course, when it comes to test, you will either see whether the flow is steady or non-steady. Non-steady, then you need to calculate this dimension. So for this early stage of this module, we will always consider steady. As we learn more and more things later on, this one will not, we will calculate this component. Okay. At this moment, we will assume this one steady. So we only left out the control surface. So control surface, here the flow cannot go out. Here also the flow cannot go out. The wall, everything cannot go out. Here the wall also cannot go out. Here also cannot go out. Here also cannot go out. The only thing that can go out is here, section 1, section 2, section 3. So the control surface that having flow that cross them will give you this equation. All right. Now, how you write the positive and negative sign, I already teach you how to draw the vector diagram. Okay, the first one is negative for inlet. Positive is out. Huh? Positive is out. So at this stage already, you should know what happens if you have an inlet. The m dot will be negative. When the flow is flowing out from the system, it will be positive. So just recap for section 1. The first step, you draw the opening. The second step, you include the volume. Okay, you include the volume. Include the volume, and then the third one, you draw the area opening, this one. Okay, so the area always pointed to the opening. So A is pointing out like this. If you look at section 1, it's opening to left-hand side. So then you look at the arrow. It is opposite with the dot product, then the product of this one will get negative V dot A. VA. Okay. For section 2, you draw the opening. You draw the velocity vector U, and then you draw the area, and this area is opening to the right, so you just draw an arrow of your area, opening A. And you're seeing these two arrows go side by side, it will give you a positive value, so positive 2A for number 2. You do the same for number 3. 3 velocity following out. U. Area always pointing out. So velocity times area, same arrow, will give you positive value. So it will tell you positive or negative sign when you do the analysis. Okay, so after you write the continuity equation, arrow steady, here you score 1 mark, arrow steady another marks. Derive this section, this component. This one consists of all the opening. Rho V dot N, the A is actually a M dot. So inlet is negative, outlet is positive, outlet is positive. This one, another marks. M dot is not the only mass, it's the M dot, mass flow rate. Okay. Okay, this equation is defined by continuity equation. Then after that, you rearrange this equation because we want to find what is our M2. Why? Because M1 is given value already. Your M1, M dot 1, section 1 is given 300 kilogram per hour. And your outlet number 3 or section 3 also given the value, right? Mass flow, the mass flow rate at section 3 is 1.5 kilogram per hour. So you have these two. This is missing. So from this equation, this one is given, this one is given, this one is missing. So you rearrange the mathematics structure. You have M2, M dot 2 equal to M3 minus M1. Substitute the answer. M2, M dot 2 will be 298.5 kilogram over hour. Okay. Any questions so far for the first one? Quite direct, right? Any question you want to ask me? Any of you? No, then we move forward. Stop me if you're not able to understand what is happening on your screen. Just stop me and ask me a question. All right. Now, I take this question further a bit, especially when it comes to your test or final exam. There will be a special section that will ask you, give you a scenario. What if the coil is included in the control volume? It means that you need to redraw your control volume. It means that your control volume is included into the control volume. So they are, if you included the coil, meaning you have another two opening here. You have another two opening. So if you look at the coil here, so what is in will always give you negative sign, out will go positive sign. So if you don't know, you just draw the diagram. Velocity going in, this is 0.4, this here, 0.4. So velocity going in. Okay, so since it's in vertical, I will just use V lah. V for represent the vertical direction. And the area always pointing out. The opening always pointing out, A. So if you look at the products of these two arrows, it will give you negative sign. And if you look at station 5 or point number 5, so the velocity will come out, V. Arrow always, area always pointing out from the surface, from the to the opening. So if you look at these two arrows, same direction, it will give you positive. Okay, this is how you read the diagram. Okay, so you need to define, or normally you will mention in the question, you will mention that if you need to consider the flow from the coil, then 1, 2, 3, 4, 5 will be steady flow. Okay, we assume that we're having a steady flow. In the real scenario, of course, you won't have a steady flow. However, for this tutorial question, we will assume it's steady. So again, write the continuity equation again with the integration of your control volume and plus the integration of the control surface here equals 0. And since you're using the steady word, draw the arrow, write steady, you score some marks for this effort. Then this component, the control surface component, you have 1, 2, 3, 4, 5 because you have 5 opening. Control surface basically is look at your opening. So section 1, section 2, section 3 now added another 2, section 4 and section 5. So by this, at this moment, you should understand why for point 1 is negative, point 2 positive, point 3 positive, point 4 negative, point 5 positive. Okay, so by looking at this equation, you already can know how many input and how many inlet and outlet you have. So negative, negative, you have 2. It means you have 2 inlet, you have 3 outlet here. Okay. Then still, you look at the M2 again, which is here. Here is missing. So M4 and M5 in the question. In this case, all right, we included 4 and 5 here. So as you can see here, M4 and M4 plus M4 minus M5. So although there is no value given in the question, so if you have a steady system, meaning the M dot 4 m.5 will be equal, meaning there's no leakage inside the pipe here. There's no leakage, and the mass is steady from the in and out. So m4 equal to m5, then you can cancel 4 and 5. At the end, you still arrive at m2 minus m1. Okay, so remember, this kind of question will be appeared in your test or exam. Of course, when it comes to exam, this one might not stable. So this one in this tutorial is steady. So when it comes to test, this one you need to look at the question. Sometimes M4 and M5 will be given. Then you need to substitute the value inside here. Then you get M2. Okay. Any question for tutorial question number 5? If no, then we go for the next one. Is it clear? Now, question number 5, this one, I do not do the detailed substitution there. So you need to do it yourself at your site, at your revision. You need to know how to substitute the answer. Of course, in the exam, you need to substitute to get the full marks. Okay. Look at the second question for today. All right. Now, second question today will be a bit similar to the previous one in your tutorial question number 4. However, this one, we take this one a bit higher, the level a bit higher, where we look at 3D scenario. Okay, a 3D scenario. So the question go like this. You have an incompressible. This is a very important word when you try to solve fluid mechanics question. Given incompressible laminar water flow developed in the straight pipe. The word straight also help you a little bit. Having radius r, this question give you r instead of diameter. Indicate in the picture below. At section 1, velocity profile is uniform. So by looking at the diagram, you know that you have a straight line. Then this one represents uniform flow. Velocity is equal to a constant value u here. And it's parallel to the pipe axis. And then section 2, velocity profile is asymmetric and parabolic. So you have seen parabolic, and there's an equation given in the diagram. U2 equal to U max times the 1 minus r divided by r squared. With zero velocity at the pipe wall and the maximum value of U max at the center line. So mean that section 2, the velocity at here will be 0. Velocity at here, at the center of the pipe there, you'll get U max, maximum velocity. Okay, if you already learned in your introduction to fluid mechanics, then you know that you have a friction on the wall here. Then when you have a friction, the contact point between the fluid and the surface will give you 0 velocity, okay, at the wall, okay. And as the distance increase to the center, then there's less and less friction, and at the center, you get the maximum velocity at the center. Okay. Now this question asks you 2 things. It asks you to derive an equation to relate U and U max. To relate this one, section 1 velocity and the U max in section number 2. It asks you to derive equation from a continuity equation. How are the average velocity, V2 and U max related? Also derive equation by using this diagram. Okay. Before we proceed, we look at some keyword in the question. So the first one is incompressible. So when you have incompressible, your rho or your density will be constant. So in your answer sheet, you write incompressible flow, meaning rho equal constant, you get 1 bonus mark there. Okay, so this one will help you score some marks there. Okay, yeah, okay, the rest I will explain later. Let's try to solve the first one. How we relate U, this one, with U max at the center here. Okay. So the first keyword we use incompressible alumina. So since we are deriving equation from chapter 2, or from this chapter, so you write continuity equation, and continuity equation will be integration of control volume plus integration of control surface. Be careful on the volume and velocity symbol in your answer. Okay, del over del T, and this one you need to write like this. Don't write this, or don't use the capital D. Okay, if you write D or capital D, I'll give you wrong answer for equation. It's a partial differential or small changes of the mass to the time. Okay, so be careful on the symbol that you use. Once you write the continuity equation, the next step, by default, by automatic, you should know. The next step is that you draw an arrow, write steady, you score in the marks for this one. Then you focus on control surface only. Okay, so control surface is about the inlet and outlet. So you only have one inlet, one outlet. However, the flow is not same. One is uniform flow, one is a parabolic flow or non-uniform flow. Okay, how do we solve? So we extend our understanding from the question. So section 1, U1 equal to U. So you do the inlet first. All right, you do the inlet first. So this one, you know that this component consists of how many inlet plus outlet equals 0. So you calculate the inlet first. So the first one, we look at inlet 1 equal rho v dot n vector direction, the A equal minus rho 1 A1 U. You should already understand why there's a negative there already. Okay, you draw section A, section 1 or section A. So this is your area. Okay, the flow coming in, U, area always pointing out. This is your area vector. So U times A, different the arrow, give you negative sign. So you explain why there's a negative there. Okay, and also is an inlet. So inlet will always negative for the M dot, yeah? For the M dot, negative. Rho 1, A1, U1. So we have the first equation already. This one, another point for your answer. Okay, anyone have question? Anyone don't understand why you can write minus rho 1, A1, U1? Anyone have question?
No questions, sir.
Okay, good. So this is just another highlight. I already explained why it's negative there. So another one, we look at outlet already. So at outlet, velocity is non-uniform. The equation is given. So you need to derive the equation from here. So if you cut section 2, you are seeing a circle, and you at the center of the pipe there, you draw a cross. And let's say we look at very, very small area along the from the radius here. So small r is a location area, a location length from the center, denote as r. dr is the differences of the changes of radius between 2 points. And dA2, it means the area inside the two line here. Okay, the inner R and outer R. So you can calculate the dA inside here. So this one you need to recall your advanced mathematics that calculate area inside a section with the R and theta sometimes. All right, this is your S. And the area how you calculate from the trigonometry equation. For outlet number two, you write rho v, you copy the shape, the structure of the control surface equation. Outlet number two, rho v dot n hat dA equal to rho 2 A2 U2. Okay, so this is just apply what you look at the question. dA is A. Okay. And just a side note, U times A equal to your Q, volume flow rate. Q equal to UA. Or another equation, m dot equal to Q times rho Q. Okay, so these are the side equation that you should always practice and memorize. Okay, positive. You should know why positive. When you derive and you draw the vector diagram for the area and velocity, you get positive sign. Okay. Next, I will continue to expand the equation for outlet number 2. So the area for a circle is, you can calculate like this, because you need to integrate with the radius. So what you try to do here is that you pull the rho 2 out and you integrate the area. How you find the area 2? Area number 2 equal integration of dA that you see on the screen here. Also mean it's an integration of 2 pi r dr is your A. 2 pi r is your radius, circumference, times the dr. You get the area of this circle. Okay, this one you learn in your trigonometry or your advanced mathematics, how you calculate the small changes, how you integrate the area of the circle. If you're given, you need to integrate the r. So this one, advanced mathematics. So you need to go back and review. So this is the application of integration if you want to find the area. So area 2 equal to integration of from 0 to r. R is the outer diameter, outer radius, which is r here from the center. So you integrate from 0 to r, then U2 2 pi r dr. So when you integrate, you'll get some answer. So I'll not go deep into integration steps. If you're still weak in integration, go back, go Google and see some video on how people teach you to do integration. Okay. So we have done for all the outlet already. Then you combine all the equation. Okay. So combine the equation you have. This is your outlet. This is your inlet equals 0. Okay. You derive just now. Since it's incompressible, state in the question itself, rho you can take out. Rho is the same. where row 1 equal row 2. So here, when you write this statement, you get marks. So you can cancel the row inside the equation. Row 2, row 1, you draw arrow, cancel. But before you cancel like this, make sure you explain why you can cancel like that. So I'm when you draw an arrow in your answer, I'm looking for your definition for incompressible, and you write something like this. All right, row same for 0.1, 0.2, or you can write row 1 equal to row 2 to define incompressible. Okay, don't just cancel and then there is no explanation, then I'll give you wrong. I'll give you wrong for not explaining what you're trying to do in your steps. Okay. Then your answer will only have integration of 0r u2 2 pi r dr minus a1u equals 0. So you can continue to derive the mathematics model. Okay. Then the next, you just apply what is given in the question. You have u2 equal to u max bracket 1 minus r divided by r square. You just substitute this one. You will get this one. Then you move this term to right hand side. You arrive at this mathematics model. Okay, the rest you need to do the integration steps. Okay, so you know that u max is a constant value. You move outside integration. 2 pi also constant value, move outside. So at the end you arrive at 2 pi u max integration 0r bracket 1 minus r square times r dr equal a1u. Then you arrive at this one. The rest is just simplification of your mathematics steps. You done the simplification, you done the okay. Then the next step we just substitute in the r inside to begin the integration steps. So that's why in the last line on your screen here, you see a r and r cubed inside here because you want to go ahead and integrate this term. Okay. So when you integrate, you'll get r squared divided by 2 minus r4, r power 4 divided by 4r squared, and then you substitute the r and 0 for the integration products. Okay. Now, since we have an integration with the limit here, with the boundary condition here, means we don't need to find the constant value like what we did in the previous lecture. So this one, you don't need to find a constant value for integration. Straight away, you substitute. And you continue solving for u max and u. So here, you can cancel. So area for section 1 here is a full circle. So full circle area is pi r squared. Then the next, you just look at both sides, see whether you can further simplify, cancel the pi, rewrite the equation. You arrive at u max equal to 2u. So far, everything looks logic to you, reasonable to you. We have already done for section A. Okay, if no question, I'll forward, continue. So what happens if you have a B there, B for average velocity at section 2. Okay, we go for a few more slides, then we go for a short break. Yeah. Okay, so we're done with section B first. Okay, section B. Okay, maybe go for a short break. You go for a short break? or you guys can continue. Any idea?
Whatever, sir.
Yeah?
Whatever.
Continue?
Yeah, can also.
Okay. Anyone want to break? Please voice.
No, sir.
Continue. Huh?
No, sir.
Okay. So B section 2, V2 and Umax related. Want to relate U velocity, average velocity with Umax. So what we do, since it's compressible, area constant, we can write U in this form. Okay. We can use this general equation. Okay. So I'm going to explain how to. Okay, later I will. In the slide, I already prepared the derivation steps. I believe you can read right from the slides. So U2 equal to half Umax. If you know how to derive, and this one you should already cover in your introduction to fluid mechanics or something. So this one you should know. However, in my slides, I included the detail on this proving process, right? U2 equal to half Umax. All right. So the answer for section B is this one. U2 average equal to half Umax. So I just go through a bit faster since I think you already learned about this one. Okay, so you need to draw this diagram. So diagram is that you have Umax, means the maximum velocity at the center. This is your Umax magnitude. The blue color is average velocity, the blue color reason, where we want to link the red color into a blue color magnitude. So we want to prove this equation. Average, the blue color, will be equal to the red color shape. So if this diagram just tell you what happened if the average is not same as your Umax divided by 2, it means that it's not a parabolic equation. Okay, it's not a parabolic. So if it is parabolic, then you can prove Umax divided by 2. This equation only works for parabolic shape. The U2 equal to half of your Umax only happen in a parabolic shape. If it's not, then it's not parabolic. Okay, important. This one might ask you in final exam. It will ask you to explain what can you tell whether the velocity profile is parabolic or non-parabolic. Prove this phenomena. So you need to develop the equation from the diagram, and then from the final answer itself, you predict either it's parabolic or non-parabolic. So if your average velocity equal to Umax divided by 2, then it is a parabolic behavior. And if your U2 average is not same as your Umax divided by 2, then it's a non-parabolic. Okay, so this is important slides. Okay, you might need to come back to these slides later on. Yeah. So this one I just pull out from the introduction to fluid mechanics. All right. So as you can see here, you have two diagrams. So we were equaling this diagram to this one. We assume that we have parabolic shape of flow will equal to a uniform flow, as you can see from the screen here. So R, our center at the center of the pipe, X and R, and we're having a non-slip scenario. So we're going to prove parabolic flow and average speed. Both having a same pipe, and volume flow rate will be the same. Q will be the same for both scenarios. So Q for the left hand side will equal to the Q on the right hand side. And what is Q again? Q equal to U times A. Velocity times area, you get Q. Okay, so Q equal to VA, and in this case, we are looking at the average velocity diagram. So Q equal to V hat means average velocity times A. So A is a pi r square. Then you get the first set of equation for uniform flow. Second diagram is going for the parabolic shape diagram with the Umax at the center. And you need to draw the cross section of the pipe with the diagram that you saw just now, R, dr, and dA. dA, how to calculate the dA? The area will be 2 pi r times dr. So this one already proven in your advanced mathematics class. dA equal to 2 pi r dr. You integrate the total area, means that you integrate both sides. Integrate 0 to r for 2 pi r dr. So Q equal to VA, and since we know that Q equal to VA, you substitute the area using this equation. So Q equal to V integrate of 0r 2 pi r dr. Okay. So you use a second order equation. What I mean by second order equation? Because we want to find the velocity, and this velocity is changing, so we call it as a variable, and it's having a parabolic shape. So parabolic shape equation give you by this equation, general equation, V equal to AR square plus B. Okay, this is a parabolic general equation in the second order equation. So you have third order, fourth order. This one is in the second order. Okay. So you need to find what is your A, what is your B. So when R equals 0, which is at the center, or at the center, your velocity is maximum at the center. When your R equals 0. Okay, so you substitute inside here, use this 3 equation, R0, V, Vmax. So your B is Vmax at R equal to center. What happened at the edge here, at the wall here? At the wall there, or outer, at this area, your R equal to outer R. Velocity at the wall here, and we know that the contact between the float and the surface is 0. I mean the velocity will be 0. So V will be 0. So you substitute this one into the parabolic equation. R here, V0. You get your okay. Then you have your B just now. You just use back the B. So you get what is your A. Your A equal to minus Vmax divided by R square. You rewrite what is your A and B into the parabolic equation. You arrive at the capital V, velocity for the parabolic. V equal to minus Vmax divided by R square plus your B is Vmax. After that, you substitute inside the Q equal to VA equation just now. And again, we are looking at parabolic scenario. So we are using this equation, Q for parabolic side. And in the beginning, we compare uniform flow and parabolic flow. We have 2 equations. You put 2 equations side by side. These 2 side by side. And you can rewrite them. So you factor out the Vmax from the equation just now. Vmax equal to 1 minus R square divided by R square plus 1. So you just continue doing the integration. Okay, I will skip for explanation for the detail. You look at the slides. At the end, you do the integration steps. You substitute the r and 0 inside there. You get this form. Okay. You simplify the equation. You get this one. You equal the both q. Further simplify again. Because you this one then 2. Then you move side by side. Okay, this one is symmetric, uniform flow. This one is parabolic flow. This one is here. This one is here. So you cancel both side equation. The pi cancel the r. At the end, you arrive at v hat equal to u max divided by 2. And this one only works for parabolics. So if this one is not same, then it's non-parabolic. Okay, this is how you prove. Okay, I stop the recording here. We go for a short break, and then we come back for our third example. Let me stop recording.